Okay, so moving on to Green's functions. So right away, before we start, I'm going to tell you right now, this is going to be optional. Just like section 4.5, it's not going to be required. It, so Green's functions are typically a more advanced topic. This is something you might see in a course on partial differential equations, or maybe in a mathematical methods of engineering course. So if you go on further, you will see these types of things eventually. These Green's functions, but they're not typically covered in a first semester of differential equations course. At least it wasn't when I first took this course. So that said, I do want to at least give you some flavor of why this is important and where this could come up later. So I'm going to start with just the variation of parameters, right? Remember, we're solving this differential equation, second order differential equation, and we get this solution. This is a general formula for the solution, right? Written in terms of the integrals here, right? So the first observation is that the C1 and C2 here will depend on the initial conditions. And we can arrange the initial conditions so that the C1 and C2 are both 0. Okay, so let's assume we've done that. We have some initial conditions which allow C1 and C2 to both be 0. So now we can write down the solution this way. Y of x is going to equal the definite integral from 0 or x0, either way, to x of negative y1 of x. Now notice that t is the dummy variable here, right? So it doesn't depend on x, which means you could bring the y1 of x inside the integral, and it's not going to matter. Oops, sorry, not f of t yet. Y2 of t divided by the Wronskian w of t, right? And then likewise, you can also bring the plus y2 of x inside times y1 of t, right? And then just add, because we have the same denominator, w of t. Now, all of this is going to multiply f of t here with respect to t. Okay, so now we have our solution in a somewhat more compact form. Again, assuming that these c's are 0 here. So yeah, this is a particularly nice way to write it. In particular, notice that all of this, right, is just some function of, well, it depends on both x and t, right? So this is a function of x and t, and we're going to give it a name. We're going to call it g as a function of two variables, x and t, right? And so here it is again, right? It's just negative y1 of x, y2 of t, plus y2 of x, y1 of t, that's an x, all divided by w of t. Remember, w is the Wronskian. Okay, so yep. So this is what we call Green's function, right? This is Green's function here. Or I should say that it's Green's function for a particular linear operator, right? So the linear operator here, in this case, is, I'll call it L. It's just going to be the second derivative with respect to x plus p of x times the first derivative with respect to x plus q of x. Okay? And so here's the idea, right? If we apply this linear operator L to, let's say, y, right? This is just going to equal all of this, right? It's going to be y double prime plus p of x times y prime plus q of x times y, right? And so this differential equation up here can now be written as L of y equals f of x. So f of x being the non-homogeneous part, non-homogeneous part, right? So this, again, right, so this equation here, and the idea is we want to solve this equation for y, right? Now remember, this is an operator. L operates on y. It's not L times y, so obviously we can't just divide by L. That doesn't make sense here. But in some ways, we want to undo this L, right? We want to, right, at least formally, write y as the inverse of L applied to f of x. Okay? And if we can do that, then we have our solution for y. And in fact, we just did that, right? This is our y of x, right? So this inverse operator L, if this is L here, then the inverse operator L inverse applied to f of x is really just this integral here. It's the integral from x0 to x of, well, let's write Green's function as x of g of x and t times f of t, oops, sorry about that, times f of t, right, with respect to t. And when you evaluate this integral, right, it's going to be a function of x, right? So this will be y of x. Okay? So that's the power of these Green's functions. It allows you to write the solution to this differential equation in this very compact form here. Okay? And I mean, I don't know how much further I want to stretch this. So if you apply L to Green's function itself, and right, so we take L of g of x and t, we get something called the delta function. This is the Greek letter delta of x minus t. Right? So again, I don't know how much further we're going to get. I don't know if we're going to be able to talk about delta functions in Chapter 7. But that's what you get when you apply this linear operator L to the Green's function here, right? You get the delta function, which is not really a function. We call this the Dirac delta function, but it's not really a function. We still call it the delta function for historical reasons because Dirac came up with it and called it a function. Later on, mathematicians were able to sort of make this more rigorous and formalize it, and that leads to the theory of distributions. So it's really a distribution, not a function. But again, we're not going to get too deep into that. This is way more advanced. This is a course in functional analysis. We'll cover distributions. But so the reason why this is not really a function is, and this is not how it's defined, but informally we can say, look, this is equal to 0 if x is not equal to t, right? So when t and x are different, then it's just 0. And when they are equal, if x does equal t, this is just infinite. It's defined to be infinity, which of course doesn't make sense, right? That's why this is really not a function here, right? The way it's defined is in terms of this integral, actually, right? But let's not get into that. I think I better just stop here and leave it at that. Yeah. So one thing about this Green's function is that it doesn't depend on f of x. It doesn't depend on the right side, right? Obviously, when you find the solution, when you find your y of x, it'll be in terms of both Green's function and the right side, your f of x. So that will come into play. I'm going to leave it at that. Like I say, this is optional. We're not going to go any further with this. So let's just move on to section 4.9.